Question 16. So with mathematical induction, what you want to do first is show that the statement is true when n equals 1. So you can say when n equals 1, on the left-hand side, 3 to the 1 is just 3, so we've got x to the 3 minus 1. And then on the right-hand side, we have x minus 1. Let's just see where we need to end up, what the last term is. So you've got 3 to the 1 minus 1, so 3 to the 0, which is 1. So that's just 2. So we get x squared plus x to the 1 plus 1. So that's actually this one. So that's the last one in the sequence. And then what I would do is just expand this and show that it's the same as that. I think in the solutions they factorized this and to show that it was the same as this. But equally valid just to expand this. And then we can simplify this because that cancels with that and that cancels with that. And we get x cubed minus 1, which is the left-hand side. Okay, that's that bit done. So now what we want to do is show that if it's true for n equals k, then it's also true for n equals k plus 1. So you can say if x to the 3 to the k is equal to all this, 2 times 3 to the k minus 1, so x to the 3 to the k minus 1. Okay, if that's true, and then we need to derive some things from that fact, assuming that that's true. So where we need to get to, like what I would do in my rough working, or just keep in my head, is that what we want to prove is that this is true when n equals k plus 1. So we want to show that x to the 3 to the k plus 1 minus 1 equals, all of that up to x to the 2 times, so k plus 1 minus 1, which is just k, x to the 3 to the k plus 1. We want to show that that's true. So the way that I did it was that I just figured this is just that, but multiplied by this extra bit. We just sort of tack that on to the end. So what we could do is just multiply both sides of this equation by that. So you could say, okay, so if that's true, then x to the 3 to the k minus 1, that times, what was it? X to the 2 times 3 to the k, that's x to the 3 to the k plus 1. So just multiplying both sides of the equation by that. So times all of that, times that one. I might just leave that out because I'm going to run out of space. So okay, so that equals all of that, which is just this multiplied by that one. And then on the left, let's expand this. So we want to show that it's the same as this. So we will have x to the, so this one times that one is like x to the 3 to the k plus 2 times 3 to the k. And then you've got that one times that one, so x to the 3 to the k plus 3 to the k. And then that, and then minus, a lot of writing in this one. Okay, so we've expanded that, and then on the right it's just the same thing. I'm just going to write ditto there, ditto marks. I wouldn't do that in exam, I'd probably bother to write it out, but I do dittos in my rough working a lot when something's the same. Okay, so we just need to simplify this. We have an x to the 3 to the k there and there, so those cancel. And then this is 2 times 3 to the k up there, so that one cancels with that. And we're just left with those two. So we've got like a 3 to the k plus another 2 3 to the k, so that's 3 times 3 to the k. So we have that equals ditto. And then think of that as 3 to the 1 times 3 to the k. So that'll give you x to the 3 to the k plus 1. And that's what we were trying to prove. So the way that I did it is different from how they did it in the solutions. What they did is they said this is x to the 3 times 3 to the k, and then that's x to the 3 to the k cubed. So what we have there is just that, and then they factorized this. So you can do it that way instead. I find this sort of more straightforward. Just like do something to both sides of the equation that's going to give you the next one in the sequence. It tends to work most of the time. Okay, so that's pretty much it for that one. Then you can just have like a conclusion line which says something like, therefore, by mathematical induction, this is true for all n greater than or equal to 1. Part B. So I think this one was tricky just because there's so many things that you could do. Like there's so many different similar triangles and congruent triangles and things that you could do. Like I had a lot of ideas about how we could show that those two are equal. Like if we showed that dz was equal to ye, maybe by showing that those two triangles are congruent, that would prove it. Or if we could show that that is a parallelogram and that's also a parallelogram, and then therefore that's equal to that and that's equal to that, that would give it to us. But I think probably the easiest way to prove it that I settled on at the end was actually the same as what's in the solutions, which is just to use the fact that that's a parallelogram and that's a parallelogram, and then therefore that equals that and that equals that. So if we can prove that that equals that, then we're good. So how do we do that? Well, if we can show that these two triangles are congruent, then that would give us that that distance is the same as that distance. So that would show that these two are equal. So let's give that a go. So if we want to show that these two are congruent, we could show that each one is similar to the big triangle. And then we've got that factor of root 2 that they told us. So this one is like root 2 times smaller than that triangle. And that one's also root 2 times smaller than that triangle. So that means they're the same size and they're congruent. So let's set that out. So maybe we could start by showing that that one is similar to that one. So you could say you've got that angle is common, and then we could say like that one is the same as that one because of the parallel lines. So we could say something like angle BGF equals angle BAC because they're corresponding angles. So I'll just write corresponding angles because GF is parallel to AC. And then we've got angle B is common. And so from that we could say triangle BGF is similar to triangle BAC, angle, angle. And we can say that, what was it, AC on GF is root 2. That was given. Now, what we want to get to is that BF is the same thing as HC. So so if AC on GF is root 2, that means that BC on BF is also root 2. So I'll write that down. BC on BF equals root 2 because they're corresponding sides. I might write that as well. Corresponding sides of similar triangles. And then from there you can rearrange this to get BF. So BF is BC on root 2. Now we want to do the same thing with triangle IHC to show that HC is also BC on root 2. And that proof is going to be like pretty much exactly the same as what I just did there. So instead of doing that all over again, you can just say similarly, what was it? HC. HC is also BC on root 2. Okay. And then we want to show that that one equals that one. So that one is just that whole thing minus HC. So we could say, we need to look at the diagram and write at the same time. BH, so BH is BC minus HC. And then, oh yeah, and then so you could say, and then that's BF. So I can replace HC in this equation with BF. So we could say BC minus BF. And then BC minus BF is FC. Okay, so now we've shown that BH equals FC. And now we just have to say that these are parallelograms. So that equals that, and that equals that. So I might just start writing it up here so we can look at the diagram as well. So we can say, because BC is parallel to DE, that was given, and AB is parallel to IH, then that tells you that this is a parallelogram. So BDYH is a parallelogram. It's a nice little shorthand. And then you can, yeah, same thing there. So again, you can just say similarly, ZFCE is a parallelogram. Oh, actually, we could just say, we could do, instead of doing that, we could say, like, therefore dy equals bh, and then we can say similarly. So using that exact same argument, ze equals fc. And then back here we proved that fc equals bh, and then we've just proved that that's dy. And then I think that was what we were trying to show. Yeah, dy equals ze. Okay, so that's it for that one. I really think that is the simplest way to show it. I'm not sure if there are any other good ways. I couldn't really think of any other ones that weren't super long. Okay, let's do part 2. Exact value of the ratio yz on BC. So what I would do there is just try to write yz in terms of BC. So we can work out, we know that like BF was BC on root 2, and then from there you can go like FC is that minus that. So you know what, I'm just going to write it over here. So we can say we've got BF is BC on root 2. We showed that in part 1. And then you can say FC, so that bit is that whole thing minus that. BC minus BF, which is BC. So we've got BC minus that, so that'll make 1 minus 1 root 2 times BC, if you pull the BC out the front. Okay, so that's FC, which is equal to ZE. So ZE. And then we can say, oh, and we've got the DE. DE is also BC on root 2. That was kind of given up there. Okay, so we've got that, and then we can say that YZ is dE minus these two. So minus, and they're both equal, so I'll just say minus 2ZE. So BC on root 2 minus 2 times this. And I am running out of space. So let's pull the BC out the front. We've got 1 on root 2 minus 2 and then plus 2 on root 2. So let's rationalize the denominators there. We've got, well, let's actually move the BC over the other side. So YZ on BC. Just get rid of that. And then we've got, that makes root 2 on 2. And let's make everything a fraction over 2. So that's 4 on 2. And then that one is 2 root 2 on 2. So we've got, that makes 3 root 2 minus 4 all over root 2. So that's it for that one. I just noticed in the solutions they didn't rationalize the denominator. So they got 3 minus 2 root 2 over root 2, which I would say is not really correct to leave it in that form, but whatever. Part C. So let's start by working out the relationships between alpha, beta, gamma and these coefficients. So if you forget how to do that, you can always go back to saying that it's x minus alpha, x minus beta, x minus gamma, and then if you expand that, you get x cubed. The x squareds, there's going to be negative alpha minus beta minus gamma. And then with the x's, there's going to be alpha gamma plus beta gamma plus alpha beta. And then the constant term is going to be minus alpha beta gamma. So if you practice, you can be able to do that quite quickly, even just in your head. So I think that that's better than memorizing what they are. But yeah, I suppose memorizing them is faster. Okay, so from that we know that that is 0 because there's no x squared here. That whole thing is p, and that's q. So we've got alpha plus beta plus gamma is 0 from that. From that we've got that p equals alpha gamma plus beta gamma plus alpha beta, and that was with beta. And we've got that q is negative alpha beta gamma. So at first I was a bit confused about how to get this, and then I just decided to try to get everything on this side in terms of beta and gamma, and then hope that it turns into that. So you could say so the right hand side, alpha squared plus 4q on alpha, that equals, we could replace that with negative beta minus gamma, just from that equation. And then the q is negative alpha beta gamma. Oh, there was a 4. So we've got that. And then we just have to simplify this and hope that it turns into that. So that's beta squared plus 2 beta gamma plus gamma squared. And then this, that cancels with that. So we've got negative 4 beta gamma. And then that makes beta squared minus 2 beta gamma plus gamma squared. And then that's beta minus gamma squared. So that's it for part 1. Part 2. So I actually felt that this one was also a bit tricky, certainly harder than the 2016 and 2017 exams. So either I'm slipping or these exams are getting harder. But okay, first thing is, how do we use part 1 in this? So if we know that those are the roots, then we can replace these with, so that one is the same as this. And then that's going to be the same as gamma squared plus 4q1 gamma, just by like doing a similar argument to how we got that, and beta squared plus 4q1 beta. So those are the three roots of the cubic equation that we're looking for. And easiest way to work that out is just to say let y equal, so just this with x instead of alpha. And I'm always really bad at explaining why we do that, but if you want to, like, if you're confused about that, then maybe go back to question 5 on the 2017 exam, or question 15A on 2016, where I explain that as well as I can. So I'll put a link to those up there. Okay, so we say that, and then what we would like to do is to be able to write x in terms of y so that we can sub it in there and just have, so like the original cubic with the roots alpha, beta, and gamma is like x cubed plus px plus q equals 0. We want to have like that in terms of y instead, and hopefully we'll get a cubic out of that that we can look at the constant term of to work out what that is. So we've got a bit of a problem though, that like we want to solve that for x so that we can sub it in there, but it's horrible. So we're going to have to be a bit smart about how we solve that for x. So what I do whenever I've got an equation with a fraction in it, I usually just multiply both sides by the denominator, because that just cleans everything up. So we've got yx is x cubed plus 4q. And then what we could do is use this to replace the x cubed, because that's our problem here, that's what's making this equation so hard to solve for x. So if we just say that the x cubed is negative px minus q, just for moving that over that side, then we've got a much nicer equation. So we can solve this for x. Let's move all the x's over one side. So on the left we'll have a yx plus px, so let's turn that into y plus px, and then on the right we've got these, which make 3q. So we can say x is 3q over y plus p. Now we can sub that into this. So we can say 3q over y plus p cubed plus p times 3q over y plus p plus q equals 0. So now we just want to manipulate this until it turns into a nice cubic with like y cubed plus something times y squared and so on. And then we can read off the constant term. So again, you've got an equation with fractions in it. Let's just get rid of all those fractions. Multiply both sides of the equation by y plus p cubed, and that'll kill all the fractions. So that bit makes 27q cubed. We have a 3pq there, and then like when we multiply that by y plus p cubed, like one of them is going to cancel with that one, so you'll get y plus p squared, and then we've got q times y plus p cubed. So we just need to expand all of that. So we have 3pq y squared. So that makes, you can do this in 2 steps if you want, but I'm just sort of rushing it. That's y squared plus 2py plus p squared, and then we multiply it by that. So we've got that times that is that one, and then 3pq times that is 6p squared qy. And then we've got a 3p cubed q. And then over here we've got qy cubed plus 3 qy squared p plus 3 qyp squared plus qp cubed. That equals 0. And then we just need to simplify this. So we're really just interested in the constant term. So we, oh yeah, also we've got, you know, what I could have done is just divided everything by q. Yeah, that would have been smarter. But we can do it now. Let's just divide everything by q. So that'll be squared. Get rid of all of those. So because we're only interested in the constant term, I don't really care about all these y squared. So I might just say dot dot dot. I don't really care what it is. Let's just look at the constant term. So there's a 27 q squared there. We don't care about those. We've also got a 3p cubed from there. Don't care about that one or that one or that one. And we've got another p cubed there. So we've got that is the constant term, and it's 27q squared plus 4p cubed. Okay, so we were trying to show that the product of all these roots is equal to negative that. We're pretty much there. Now you can just have a conclusion line, basically. Like, we've shown that that's the constant term. So then you can just say, therefore, that. And that's it for that one. Part 3. So with this one, because I don't want to have to write this out a bunch of times, I might actually like give that a variable. So I would call that capital pi, because that's often used for a product, the same way that sigma is used for a sum. So we can say let pi equal that, and then I won't have to write that whole thing out again, which will be convenient. So let's see what happens if this is negative. So if 27q squared plus 4p cubed is less than 0, what happens here is that we've got a negative here, and then negative of a negative is positive. So we will get that that product is positive. All right, let's think about how we're going to show that we've got 3 distinct real roots. Now, distinct means that like alpha is not equal to beta, and so on. So you can see here if alpha were equal to beta, this would be 0, and then that whole thing would be 0, and we know that that's not true because we've got that it's greater than 0. So we can start out by proving that they're distinct quite easily. We could say something like, since pi is not equal to 0, alpha minus beta can't be 0, and beta minus gamma can't be 0, and gamma, blah. I started out writing alpha and then it just... Gamma minus alpha can't be 0, and then, so let's just rearrange these. Alpha is not equal to beta, beta not equal to gamma, and gamma not equal to alpha. Or you could just write it out as a sentence. You can say something like, if any of the roots are equal to each other, then pi will be 0, and we know that that's not true, so... okay, so therefore the roots are distinct. Now, onto the real part. What you could do there to prove that they're all real is assume that that's not the case, and then show that that leads to a contradiction. So we could say, like, if some of the roots are complex, then what's going to happen? Because this is a polynomial with real coefficients, then that means that the roots have to come in complex conjugate pairs. And because there's 3 roots, one of them would have to be real, because you can't have like 3 things all paired off. So you'll get 2 that are complex conjugates of each other and 1 that's real. So you can say something like, just like write out in a sentence, if the roots are not all real, then you'll have a complex conjugate pair and 1 real one. And then what I want to do is like set one of the roots to be a plus bi, like give the real and imaginary parts names, and then sort of simplify this and see what we get. And we're expecting to get that it's that this will be actually negative, and that that's going to be the contradiction because we know that it's positive. So what we can do is just say, like, let alpha be a plus bi, and then beta could be its conjugate, a minus bi, and gamma would be the real one. Now, you might be thinking, like, aren't I making an assumption there that alpha and beta are the complex ones and gamma is the real one? Yes, but it doesn't really matter because alpha, beta, and gamma are, like, interchangeable. There's no difference between them up to this point. And in mathematical proofs, there's a special set phrase that we use when we're making an assumption, but it doesn't really matter. And that phrase is without loss of generality, meaning, like, yes, I'm restricting things here, but it doesn't actually really matter. And you just abbreviate that with WLOG, without loss of generality. I guess they probably don't teach that in high school, but that's what I would do at university level anyway. Okay, but you don't really need to say that. You can just say, like, let alpha be that, and so on. All right, so now we can work out what this is in terms of A and B. So now here's where it helps that I've defined this thing and I don't have to write this out again, which is very helpful in an exam to save time. So we've got alpha minus beta squared times beta minus gamma squared times gamma minus alpha. Now, in this part, the a's cancel, and we're just left with 2bi, and that's squared, so that'll make negative 4b squared. So we're expecting that this part here is going to be real and positive, because that's going to give us the contradiction that's going to make this negative. So let's think about what this is going to make. I would sort of see this as, like, I would group the real parts together because we know A and gamma. Oh, I probably should have said something here with about A and B being real. Okay, so let's group the real parts. So A minus gamma, and then you've got minus bi. So that's that part. Now, with this part, we've got, like, gamma minus A minus bi, which is kind of annoying because it's almost the conjugate of this. Like, the conjugate of this is A minus gamma plus bi, and that's the negative of that. So that's kind of annoying. What they did in the solutions was, I think that they started out by saying something like that, that gamma minus alpha squared is the same thing as alpha minus gamma squared. So you could do that if you like. If you started doing this in your rough working and then you, like, backtrack and plan ahead. But what I might do here is just say that this is the negative of the conjugate of this. So then I can say that we've got, so that negative, when you square it, is just going to disappear, which is why you can say that gamma minus alpha squared is the same as alpha minus gamma squared. But now what we can do is kind of, like, bring these, like, put the square on the outside, if you know what I mean. So we've got A minus gamma minus bi, and then this bit, A minus gamma minus bi conjugate. I hope that made sense to you. If not, leave me a comment and I'll try to explain it better than my current rambling. So now we've got a complex number times its conjugate, so that'll give you the modulus of the number. So that will be real part squared plus the imaginary part squared. So now that's really good because we know that this is a positive real number. So that means that this product is less than 0. So you don't really have to justify that. We can just say that's less than 0. It's because we've got squares of real numbers here. They're always going to be greater than or equal to 0. Actually, I suppose that could be, maybe I should say less than or equal to 0 rather than less than 0. That's fine, that's still a contradiction. Okay, so, yeah, then that's pretty much it. We could say, you know, therefore the assumption that they could be complexes is wrong. So, yeah, or you could say, therefore, the roots are real. Yeah, and that's it for that one. So this exam had a few hard questions that took quite a lot of creativity to solve. And I think the key to those kinds of questions is just keeping a playful attitude. Like, the more that you focus on, like, you know, oh, I have to get this, you know, time's running out, I have to get a good mark in this exam, the more close-minded and inside the box your thinking gets, and then you can't make those creative leaps. What you need to do is just treat it like a game and just play with ideas, and that lets you be more creative. And what else really helps is just having experience with recreational mathematics and problem solving. So I'm planning to do more of those questions from the past Australian Mathematics competition papers, which are really good for training that sort of creative problem solving skills. So stay tuned for those. And if you haven't already watched my 2017 or 2016 Extension 2 exam videos, then check those out as well.